Let's now go back to this idea of solving quadratics. So here's a quadratic equation. Normally we'd say, well, what multiplies together gives 7, adds together gives 3, and of course we're struggling to find a solution. So we would jump to our quadratic formula. Now in the past, this would present us with a problem. Square root of negative 19. What do? It means there's no solutions. Well, now there are solutions, because we can simplify that surd, and it becomes the square root of 19i. Some people like to put the I out the front. So yeah, we got two answers there. Negative 3 plus the square root of 19i over 2, and negative 3 minus the square root of 19i over 2. Of course, another way we can now do quadratics, it means every quadratic can be solved using the idea of completing the square, because we can always create now the difference of two squares. I would change the concept because I'm going to complete the square. We know it will be half the coefficient of x. So it's x plus 3 on 2 squared. But if I square that, I get 9 on 4, not 7. Therefore, I need to add 19 on 4. Now, in the past, that's a problem because we don't have a formula for the sum of two squares. But this is no longer the sum of two squares, because plus 19 on 4, we now know, is minus 19 on 4i squared. So we have two squares. So I can say, well, it's x plus 3 on 2 plus root 19 on 2i, and x plus 3 on 2 minus root 19 on 2i, and then we can just read the solution off quite nicely then. Oh, well, there's x. So sometimes it's quicker to do that than plugging into a quadratic formula. I guess it just depends on what the numbers are. So now let's create some quadratics. The thing is, because all of these complex solutions are coming from the quadratic formula, and we always get plus or minus the square root, we know every solution will appear in conjugate pairs. If the coefficients are real, it's possible to have a quadratic equation now where maybe the coefficient is not a real number. We'll worry about that later. But for real coefficients, we know we're going to have conjugate pairs. Therefore, I could always write every quadratic like this. If the solutions are conjugate pairs, one factor then would be x minus z, the other factor would be x minus z conjugate. And if I expand that out, I get x squared minus the number plus its conjugate, x, plus the product of the number and its conjugate. Well, what is that? Well, a number plus its conjugate, if I'm going to add those together, that imaginary part now cancels, because one's plus, one's minus. I end up with twice whatever the real part is. And z conjugate, remember we saw that, that's the x squared plus y squared, the sum of two squares. So if I now want to find in a quadratic equation whose roots are actually 4 plus I and 4 minus I can say, well, look, I know, and I probably wouldn't actually write this down, by the way. I'd probably just write the quadratic equation straight away. But what I'm thinking is, well, I know the sum is going to be 8. It could be twice the real part. And I know the product's going to be the sum of the two squares. So 16 and 1 is 17. Therefore, my equation must have been that. X squared minus twice the real part x plus sum of two squares. That must have been the equation these solutions came from. So how do we now find square roots? Because whilst we're finding square roots of real numbers, nice and easy, what about if we're now finding a square root of something that has an imaginary part? We're going to find the square root of x plus iy. The answer is going to be a plus ib. Now if I do that, how can I do it? Well, let's square both sides. If I square both sides, the left-hand side I expand out, I can equate the real and the imaginary part. So therefore, I know the solution will always end up being this. I don't do this every single time because I know that if I'm going to do it every single time, the answer is going to be the same every single time. I can simply say, well, I know a squared minus b squared will always be the real part, and twice ab will always be the imaginary part. I have to find the square root of negative 12 plus 16i. So as I say, I don't go through that whole process. I know the answer is going to be a plus ib. I'll say, well, difference of two squares, a squared minus b squared is negative 12. And again, be careful, that's the difference of two squares, not the sum of two squares. And I know twice ab will be 16. I've got simultaneous equations here. B is 8 on a substitute it into the other one, and I just got to solve. I've got a quartic, but the nice thing about this is that quartic is always a quadratic where the pronumeral is a squared. So I can treat it like a quadratic. That means either a squared equals 4 or a squared equals negative 16. Now I can reject one of those straight away. Remember, a and b are the real and the imaginary part, and they're defined to be real numbers. A squared equals negative 16 will not produce a real number. So I know that is not going to produce a solution. My only solution, therefore, would be with A, it's plus or minus 2, which means the corresponding B is plus or minus 4. I hate writing it down like that, by the way, because that sort of implies there's 4 solutions. But I guess what I'm saying is when A is positive, B is positive. When A is negative, B is negative. And so there's my solution. Now, unlike when we're dealing with real numbers, if we said what's the square root of 4, we say the answer is 2. Okay? Not plus or minus 2. The solution to the equation x squared equals 4 is plus or minus 2. But the answer to the square root of 4 is just 2. But because we can't order complex numbers, when I say the square root of negative 12 plus 16i, well, is it plus or is it minus? Because I've got 2 plus 4i or minus 2 minus 4i. Which one is the positive answer? Now, most people would say, oh, it's got to be 2 plus 4i, surely. But imagine if the answer was this. Imagine if the answer was 2 minus 4i. So then the two possibilities would be 2 minus 4i minus 2 plus 4i. Which one's the negative solution? Why is it more important for the real part to be negative? Maybe it's more important for the imaginary part to be negative. Which one is it? Don't know. Can't order them. So we always write down plus or minus when we're dealing with square roots of these type of numbers. Well, that's how mere mortals would solve it. And it's probably the way most people would do it. But there's a better way. Okay, let's go back to this problem. A plus IB is the square root of x plus IY. Okay, we just saw that. Difference of two squares, okay, gives me the real part. 2AB gives me the imaginary part. Well, let's just play with this a little bit. X squared plus y squared, what would this be? Well, it's a squared minus b squared squared plus 4a squared b squared. Play around with that. I've got a to the power of 4 plus 2a squared b squared plus b to the power of 4. Hang on, that factorises to be a squared plus b squared squared. So therefore, a squared plus b squared squared is the square root of x squared plus y squared. Ooh, that's familiar. Oh, the magnitude of the vector. It's exactly the same thing. Later we will see why it's exactly the same thing. But now we've got a much quicker way of coming up with simultaneous equations. The difference of two squares will always be the real part. The sum of two squares will always be the length of the vector. If you could imagine if x plus iy was like our vector, we had to find it. It would be the square root of x squared plus y squared. How do I know whether it's the answer, they're the same sign or a different sign? Well, this is how you tell. You look at the imaginary part. If the imaginary part is positive in what we're finding the square root of, then we know a and b will have the same sign. If the imaginary part is negative, then we know a and b will have different sign. Okay, let's now do the same example. Square root of negative 12 plus 16i. Well, I know the difference of two squares will be negative 12. The sum of two squares will be the length of the vector. Well, what is the square root of 12 squared plus 16 squared? It's 20. Simultaneous equations, I eliminate. Notice I've said a is 2 and not a is plus or minus 2. Well, I don't need to worry about the plus or minus 2 here because when I write my final answer for the square root, I'm going to have the plus or minus there. So I always just take the positive part. A is 2. Sub back in and we can work out b. B is 4. I know it's 4 because I'm finding the square root of something where the imaginary part is positive. Therefore, a and b will have the same sign. So b must be positive 4, not negative 4. I now know a and b, so there's my square root. Plus or minus 2 plus 4i. A much quicker way of finding the square root of complex numbers. Let's now look at this one where it's not a Pythagorean triad. Right? Because 4, 5, yes, 4 and 5 are certainly involved in a Pythagorean triad. But unfortunately 5's the hypotenuse, not one of the other sides. This is where it becomes a bit interesting. Okay, difference of 2 squares is 5. Oh, the sum of 2 squares would be the square root of 41. Simultaneous equation, I can still do it. A is a half of the square root of 10 plus 2 root 41, whatever that happens to be. And then I just got to substitute back in and I can work out B. B is the square root of negative 10 plus 2 root 41. Well, therefore there's my answer. Well, that is the answer. Now, people get hung up about this because you see square root of a square root. Well, so why is that wrong? It's still a number. Like, you're happy to leave square root of 2 as the square root of 2. Well, why can't I leave that one as like that? Like, that is the answer. It doesn't matter which method you use, by the way. Even if you use the original method, you're still going to come up with that answer. Right? It's a nasty question. And if they would put that in a test, you'd be going, yeah, right, good on you. Right? But there's certainly nothing wrong with that answer. All right, so let's actually solve a quadratic equation. Okay? I could go like this. It's a quadratic. What multiplies together to give 2 minus 2i and adds together to give 2 plus I? And by the way, it actually is a very simple one to work out. And we'll see in a sec when we look at the answers and go, oh yeah, we could have done that, couldn't we? But let's pretend we don't see these numbers, which actually might be reality, I don't know. We'll go to the quadratic formula. So it'll be negative 2 plus I plus or minus the square root of b squared minus 4ac. I now have to find the square root of minus 5 plus 12i. Yes, Pythagorean triad, 5, 12, 13. So the square root of 5 plus, minus 5 plus 12i, if you don't believe me, look at this. A squared minus b squared. Now have a look at the two solutions. And it kind of look, and you go, oh, hang on. I could have said just what adds together to give that and multiplies together. You could have come up with that by inspection. So if the coefficients are real, you will end up with conjugates. But in this case, the coefficients were not real. So our solutions are not conjugates. So 1b. Enjoy.